Hello, Algebra 2. We are going to get started with our last unit, Unit 9. Permutations and Combinations is our first day. Go ahead and label your paper. All right, so to get started, we're just going to consider a very basic scenario where a coin is flipped 3 times. And we want to try to think of a systematic way of figuring out the possible outcome. So, for example, if I flip a coin 5 times, what do you think the probability would be of it landing on a head versus a tail, right? So one way you can do it is with a tree diagram. You've probably done this several times before. But if you have a coin, we are going to take a look at when you flip a coin, it could either land as tails or heads, all right? And we are going to flip it 3 times, it says. So on the first time, you can either get a head or tail. Let's say, so this is coin 1. Let's say you get a tail, right? So if I get a tail, I'm following here. My second coin could also be a head or a tail, right? On the first coin, if I got a head, my second coin could still be a tail or a head. So that is my possibility for coin 2. All right, so coin 1, I could get a tail or head. Same thing for coin 2. And then for coin 3, I'm just going to make, so for if I get tail, tail, on my third coin, I could still get a tail or a head. If I get tail, head, I could still get tail, head possibilities, right? And if I get a head on the first coin, I could still get a tail on the second, and I could still get tail or head on the third. And then same thing, if I get 1 head, 2 head, on the third coin, I could still get a tail or a head. Okay, and that is coin 3. So when you draw a tree diagram, it basically just gives you a visual appreciation for what your possible outcomes are. I could either have a tail, tail, tail. I could have a tail, tail, head, tail, head, tail, tail, head, 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 tail, tail, head, tail, head, and then head, head, tail, or head, head, head. So if I toss a coin 3 times. Now notice too, a coin, 1 toss is not going to wind up affecting the second toss of the coin, because every single time you toss a coin, it's a 50-50 chance. So that's all our possible outcomes are. So what is the total number of different outcomes? Well, if I toss a coin 3 times, I could either get tail, 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 right? And I'm not going to list all of them, or I could get tail, tail, head. Okay, and then I could keep going and list every single one that we just said. So let's look. Here's 1 combination. Tail, tail, head is 2 combinations. Tail, head, tail, tail, head, head. So that's 1, 2, 3, 4. And then the same thing with the other one. 1, 2, 3, 4. So I have 8 possible outcomes. Okay? So a tree diagram is just one method of showing what your possible outcomes are. And this unit is beginning with this whole idea of probability, which is going to lead us into statistics. And this is a very basic kind of everyday scenario of what we could think of with probability. So let's go into something a little bit more difficult. The fundamental counting principle basically takes your possibilities if you have more than one object that you're looking at. So if we take a look at this example, on a weekend trip, you pack 3 shirts, okay? I have blue, green, and yellow. I have 2 pairs of pants and jeans and khakis, and I have 2 pairs of shoes, okay? What's going to wind up happening is I'm going to try to figure out what my possibilities are based on what I have here. So I could do a tree diagram. That's one method of doing this. So I'm going to start by looking at the tree diagram, but then I'm going to show you guys a lot faster way to get our total possible matches, okay? So if you're going on a trip, you definitely want to make sure you have, enough outfits for the week. So let's say we have 3 shirts. So I'm going to start with my shirts. I could either have 1, 2, or 3. So that is my blue shirt, my green shirt, or my yellow shirt. So blue, green, or yellow. And these are my shirts. Then for every single shirt that I have, I could match that shirt with 2 different pairs of pants, a jean or a khaki. So for the blue shirt, I could either put jeans on or khakis on. If I choose the green shirt, I could either put jeans or khakis on. And if I choose the yellow shirt, I could also either put jeans or khakis on, right? So we want to pick some clothes that match. Those all look like, good possibilities. Those were my pants. And now, if I choose, let's say the blue shirt and the jeans, I have two possible pairs of shoes, the brown or the black. We'll use BR for brown and we'll use BL for black. So I choose the blue shirt. The jeans, I could either put on the brown shoes or the black shoes. And that's going to happen for every single possible combination as we go down, okay? So if you guys think about it, we will basically, I'm going to just say dot, 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 because that's going to happen throughout every single one. I could have blue, jeans, brown shoes, blue, jeans, black shoes. So if you guys count every single possible combination, here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It looks like we're going to have 12 possible combinations. A little bit faster approach is using the fundamental counting principle instead of the tree diagram, and that is multiplying the possible combinations. So if I multiply the total that I have for each, I had 3 shirts, I have 2 pants, and I have 2 pairs of shoes. That gives me 12 combinations, okay? That is a little faster than having to draw out that tree diagram every single time. This is called the fundamental counting principle, and it will work anytime you're trying to put different objects together in combination. So I have shirts, pants, and shoes. We know it's fundamental counting principle because I'm trying to figure out how many combinations I can put those 3 together with. 3 times 2 times 2 gives me 12 combinations, and my tree diagram backs it up. I can look for all those combinations, all right? So this is the first method of making combinations, fundamental counting principle. Our second method of making combinations is with something called a permutation. And this is a way of, it's an arrangement of objects or things, whatever you want to call them, in which the order does matter, okay? So arrangement of objects where the order matters. So go ahead and get that written down. And take a second to read the 2 examples that we have below. All right. What I mean by the order mattering is the first example, we're trying to arrange the letters F-U-N in fun, right? So I could have F-U-N, I could have, U-N-F, I could have, let's see, N-U-F, I could also have N-F, and then U. I could also have UFN, and I could also have FNU. So if you think about all the different possibilities, right, how can we do that? So one is by listing them, and another one is by using a formula or by using our calculator. For the SOL this year, this is what your formula sheet is going to look like. You guys are going to be getting a copy of it in, when you guys come to class next time. What I want you guys to focus on is right here where it says permutations and combinations. Obviously the P stands for permutation. Our next topic is going to be the C for combination. And you have these N and R's. N is just your total possibilities, and R is how many you want to choose out of your total possibilities. So your formula for that is N factorial, this little exclamation mark means factorial, divided by N minus R factorial. So we're going to go back to our notes and try to... So in this example, our N and our R are the same because we have 3 letters and we're trying to arrange all 3 letters in different ways. So we have a total of 3 letters and we want to use all 3 letters to arrange in different combinations. So we are going to take 3 permutation 3, and this little exclamation mark again means factorial. All that means is if my N, which is 3, I'm going to multiply down to 1. So 3 starts it, and then times 2, and then times 1. In the denominator, I have 3 minus 3, that's 0 factorial. 0 factorial is the same as 1 because remember, I can't divide by 0. So 3 times 2 is 6 times 1 is 6. 6 divided by 1. So there are 6 different ways of organizing the letters F, U, and N so that you have different combinations. And again, because the order matters, that's what makes a difference between combination and permutation. Combinations we'll do next. So again, permutations, order matters. So if you think about this scenario, you have 8 finalists in a figure skating competition. They're trying to get gold, silver, or bronze. Well, the order definitely matters in this case because gold is different than getting a silver, right? So we don't want one finalist who thinks they're going to get a gold to get a silver. That is not the same. So the order does matter how we pick them. Let's try to just go straight to using our formula on this one because we have 8 finalists. So that means the first person who is a figure who gets to be a finalist could be gold, or the second person could be gold, or the third, or the fourth, or the fifth, or the sixth, or the seventh, or the eighth. So you have all these combinations. We don't want to always list them all. So we're going to go straight to using our formula. N, again, is your total. So if N is our total possibilities, that means that N will be 8 in this scenario. R is how many we want to choose. We're only allowed to choose 3 because we only have gold, silver, and bronze. So I want to choose, I'm going to put choose. I want 3 positions, okay? So now we're going to use our permutation formula. We're going to say 8 permutation 3 is n factorial, which is 8 factorial. So that's 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And I'm going to put that over n minus r. So 8 minus 3 is 5 factorial. So 5, 4, 3, 2, and 1. Notice, guys, that this is going to make it a lot easier. 1 divided by 1 can get canceled because these are all factors. They're all multiplying. We've spent a lot of time with factors this year, so we know that we can cancel out common factors. So those are gone. So that means the total number of ways that I can choose my 3 finalists out of my 8, my 3, I should say, medal winners out of my 8 finalists, is 8 times 7 times 6. So there are 336 different ways that I could choose my gold, silver, and bronze winners out of my 8 finalists. So again, these 2 scenarios, the order does matter how we choose our answers. So this is a permutation. Last but not least, we're going to look at a third way of finding different arrangements, and that is a combination. So let's look at the difference here. You have 5 people who apply to work at Harris Teeter. The store needs to hire 1 cashier and 1 bagger. How many different ways can these positions be filled? If you look at this, a cashier and a bagger are 2 totally different positions, and you might get paid differently. So the order in which you pick these people might matter. If you look down here, 5 people apply to work at Harris Teeter. The store needs to hire 2 managers. Managers are the same position. We just need 2 people to be manager. How many different ways can these positions be filled? So when you're talking about the difference between permutation and combination, in this first example, the order that we pick these people is going to be different because if I pick, John to be a cashier and Jenny to be a bagger, or if I make Jenny the cashier and John the bagger, that is going to be a different arrangement. So this is going to be a permutation, whereas the second example, where you're just picking 2 managers, it wouldn't matter whether I choose John or Jenny first because they're both going to wind up being a manager, right? So this is more of a combination where the order that I choose them does not matter. The positions are the same, okay? So positions are the same with a combination, positions are different with a permutation. So let's take a look at our last example. A team needs to select 3 seniors to be co-captains. Co-captains, it's all the same position. You don't have a master co-captain. There are 7 qualified seniors. How many different choices are there? All right, so let's look. Our total is 7 seniors. I want to choose, okay, so N and R are the same. I want to choose 3 senior co-captains for the same position. If we take a look back at our formula sheet, this is now the C instead of the P. It's still n factorial. It still has n minus r factorial in the denominator, but I have an additional piece. The r factorial is also now in the denominator. This is now the formula that we're going to use. 7 is going to be our N, and R will be our 3 because we have 7 seniors and we want to pick 3 of them to be the co-captains. Let's go ahead and substitute in. Cancel out your common factors, and we get